A quote from Andrei Kuzu states that the universe is much more chaotic than we thought, and it's too late for apologies now. The latest discoveries by the James Webb Telescope are shaking Einstein's theories of relativity, as the universe is proving to be far more chaotic than previously thought, and cosmologists such as Andrei Kuzu have long emphasized that we can no longer rely on old formulas. If we really want to uncover the secrets of the universe, we must search for new explanations. After some initial confusion, the picture is slowly clearing to reveal a dynamic cosmos and a reality that is far more fluid than Einstein's physics explained to us. The scientific drama began with Glass Z13, a galaxy that appeared to emerge from nowhere and existed only a few 100 million years after the Big Bang. The galaxy does not appear young and unstructured, but rather highly developed, star-rich, and active. So the theory of a universe that was initially empty and chaotic was already beginning to falter. This was followed by Sears 1019, a black hole so massive and energetic that it defies every model of slow growth in the cosmos, as a black hole is too young for its mass or it's older than previously thought. But no matter which version turns out to be true, the data from the theory of relativity is definitely no longer sufficient. And finally, we are dealing with a growing list of very early, very orderly spiral galaxies. Instead of the expected turbulent chaos, these galaxies already show perfect galactic symmetry, and if we believe our old formulas, that shouldn't be possible. But who is right here? Einstein and other scientists, or the universe with its facts? Science is in turmoil, as never before have so many facts spoken against a determinable and predictable universe. The strange discoveries are no longer outliers, but have become the frightening truth, and all the cosmologists who want to stick to the old standard models currently have a serious problem. For the discoveries are harbingers of a tremendous upheaval. And new cosmologists like Andrei Kuzu have long recognized a pattern in the oddities that speak a whole new language, suggesting the universe was probably never as linear and orderly as we long believed, with more and more fact from Kuzu's research suggesting that the cosmos has always been faster, bolder, and more creative than the old scientists like Albert Einstein thought. While Einstein's rules were a masterpiece of their time, now they are not enough to explain what we really see in the cosmos. The problem is further illuminated by the issue of dark matter. Did you know that the idea of a cosmos with linear, entirely predictable dynamics was made possible solely by the concept of dark matter? It's crazy. But the theory of relativity alone was never enough to explain what was really happening in the cosmos, as we often think of the standard work of physics and a few other theories have the ultimate truth at their disposal. Yet a few years after the theory of relativity was published, it already reached its limits when the rotation of galaxies showed strong irregularities in the center and at the edges that did not follow the laws of relativity. The problem eventually led to the idea of a kind of stabilizing matter that is invisible but whose effects can be observed in the cosmos, and later a similar form of energy was added, with so-called dark energy supposed to explain why the universe does not expand linearly everywhere. The currently accepted worldview is a lambda CDM model, where the Greek letter lambda stands for dark energy and CDM is the abbreviation for cold dark matter. Now it gets even crazier because imagine that Einstein's rules, which refer to the materially visible cosmos and the forces acting within it, only account for 5% of this cosmology, while 95% is made up of dark matter and dark energy. And we don't have to be physics geniuses to understand that this is problematic because the existence of both dark quantities has not been proven to this day. This leads to the S8 problem, where the universe contradicts its own instructions, and a quote from Andrei Kuzu summarizes it. If the early universe was already structured, then either our models are incomplete or nature is more creative than we thought. It's not the cosmos that has gone crazy. Our scientists were simply wrong, and some of them don't like to admit it, but it's too late for excuses now. So we need new theories, facts, and explanations. Galaxies born too early, black holes growing too fast, and orderly spiral structures emerging in a cosmic age that, according to theory, should still be dominated by chaos, all suggests that the classic idea of an orderly, uniformly expanding universe is wrong, with data from the James Webb Space Telescope suggesting that the universe is more active, faster, and more creative than previously thought. Scientist Andrei Kuzu is actually a specialist in large-scale cosmological structures and has been investigating long-standing discrepancies between mathematical expectations and observed reality for many years, with his analysis suggesting that entirely new framework models are needed, not just modifications, but probably a complete reorientation of our understanding of the cosmos. One of the main focuses of his work is the so-called S8 problem. In modern cosmology, The S8 value describes how strongly matter in the universe condenses into structures such as galaxies and galaxy clusters on medium scales at about 26 million light-years, a value derived from two factors: the proportion of total matter in the universe and the strength of density fluctuations, where the higher the S8 value, the more clumpy the universe is, or in other words, the more matter has accumulated. Scientists use two different methods to determine this value. The first is based on the analysis of cosmic background radiation, or in other words, light from the early universe, which was measured by the Planck mission among others, while the second method uses gravitational lensing effects in which the distribution of matter in the present-day universe becomes visible through the distortion of light from distant galaxies. The problem is that both methods yield different results. While the CMBB data yield a higher S8 value close to 0.83, the lens data from the late universe shows significantly lower values, mostly between 0.76 and 0.78. This deviation is statistically significant and is referred to as the S8 tension or S8 problem. The S8 problem is particularly controversial because it shakes the foundations of our cosmology, and it's clear that this issue is directly related to the current impossible observations made by the JWST in the early universe, as these discrepancies show us where the gaps in our models are, and it's precisely these gaps that scientists like Andrei Kuzu are searching for in order to understand the universe in a whole new way. If the clumpiness in the early universe is higher than expected, then this is not just some scientific curiosity, but an indication that our view of the world may be wrong, and with it our view of the nature of matter and of all creation. The observed early complexity of the universe also contradicts the assumed temporal evolution, and that means that our understanding of time could also be completely wrong. Andrei Kuzu analyzed large-scale distributions of matter using data from the DESI project and compared the data with current observations from the JWST team, which revealed that reality does not deviate only minimally from the predictions, but that the discrepancies are so enormous that they require a completely new understanding of science and cosmic reality. For Kuzu, the JWST findings are evidence of a creative multilayered early universe, showing that dark matter as an invisible binding agent may have been a gross error, and that even the basic assumption of space-time itself could be wrong. Kuzu investigated whether the universe could follow an alternative expansion dynamic, and came across a model RH equals CT that states that the cosmic horizon RH grows proportionally to time t. This concept stands in stark contrast to classical inflation, but it can explain many of the JWST findings if space-time is not smooth and continuous but discrete or fractal in structure and exhibits jumps, instabilities, and perhaps even a dynamically changing flow of time. So the picture looks very different than gravity, which has been described as a static force would not be a linear force but a capricious quantity like variable wind speeds or climatic fluctuations on our planet. The idea of redefining the entire space-time continuum is radical but necessary because the facts increasingly contradict the old models, as the universe seems to be more creative than our old formulas allow, and scientists now have to come to terms with that. This research is advanced by tools like DESI and the Lyman Alpha Forest. One of the most fascinating tools of modern astrophysics is the Lyman Alpha Forest, a multitude of fine absorption lines in the light of distant quasars caused by neutral hydrogen in intergalactic space. These lines are like fingerprints of the distribution of matter in the early universe, and they enable scientists to reconstruct structural development on scales of billions of light years. The Lyman Alpha Forest not only allows the measurement of acoustic oscillations of visible forms of matter, but also the investigation of the so-called Alko-Patinsky effect, which allows conclusions to be drawn about the geometry of space-time, and scientists such as Andrei Kuzu are using this data to accurately analyze the expansion of the universe and the distribution of matter at high redshifts in the very early cosmic era. When combined with the spectacular images from the James Webb Space Telescope, this has created a whole new picture. While the JWST shows things that clearly exist, user analyses provide clues as to how and why these structures came into being. So his work with the Lyman Alpha Forest is thus a key to questions about how and why things can exist that contradict our old ideas about space, time, and the matter within it. To reconcile observations of material reality in the early cosmos with the subtle radiation, researchers are using the dark energy spectroscopic instrument, which was actually conceived as a major international project to understand the effects of dark energy installed on the James Telescope in Arizona. DESI uses 5,000 robot-controlled glass fibers to simultaneously analyze the light from thousands of galaxies and quasars, with a goal to create a three-dimensional map of the universe that extends up to 11 billion light-years into the past. DESI measures so-called baryonic acoustic oscillations, or In other words, find density patterns in the distribution of matter as a cosmic scale for determining the effects of dark energy, and the data collected in this way not only serves to prove the existence of dark energy, but is also suitable for reconstructing the geometry of space-time itself. The first results from DESI already pointed to dark energy that is even more variable and therefore more unpredictable than previously assumed. And what is particularly exciting is that the DESI researchers were able to use the new data to prove that the previously assumed age of the universe can easily be corrected from 13.8 billion years to 15.5 billion years. Subscribe now, as the best videos are yet to come.